Good afternoon, everyone. My name is James Gaydon from Alfred H. Knight Mineral Processing. I'd just like to echo Todd's sentiments earlier. Thank you very much for attending. It's been a great turnout, and I'm sure we can all agree the talks so far have been really interesting. So, without further ado, I'd like to introduce John Webster from Golden Minerals Co., whose title is Dealing with Mother-in-Law Deposits. So I'm sure this is going to be an interesting one. John.
Good afternoon. I put an interesting title to the talk because two of the projects we have in our portfolio are from probably, as far as difficultness is concerned, probably up in the top 10%. Seems doing it itself. How'd you go backwards? Right, okay. Really, the talk's about geometallurgy, and it really should be called, in general terms, geomoney, because ore bodies are processed generally by mineralogy and not by chemistry. So if you just develop projects on just the chemical signature without knowing the mineralogy, you're in trouble. There are other aspects that are not connected to chemistry, and I'll go through that in a moment. But a lot of it is related to how you are going to process these materials. Is it going to be a chemical process or a physical chemical process to make concentrates? First project is the Jubal-Kootman project. We call this the JQ project. It's got the potential to be extremely large. At the moment, it's sitting about 900,000 ounces contained. About 250,000 is in oxide, which we are looking at putting in production in the next 18 to 24 months, assuming the board of directors goes for it. The rest is in sulfides. And when I say sulfides, there's a number of sulfides, and some of it's actually quite difficult mineralogy. We're dealing with arsenopyrite, we're dealing with tellurides, and as a sweetener, there's also a number of different types of carbon contained within the ore. So generally known as triple refractory, and hence the name of this talk. This all looks really sweet. The quartz veins are generally high grade. There is a lot of disseminated mineralisation of lower grade. The average grade deposit is around about 0.7 of a gram. Because of the price of gold doing what it's doing, the grade is now down to about 0.65 of a gram. So if you start talking about sulfides, especially complex sulfides at 0.6 of a gram, then you have to be pretty clever how you're going to make money out of that. So again, going back to just the chemistry of the deposit, you really need to take into account mineralogy. One of the things I would like to draw your attention to is this material here, this carbonaceous material. It says 2%, 2% of carbon in a rock due to its density differential takes it up to about 5% by volume. And the surface area of carbon actually can be made, especially in a grinding circuit, can be made extremely fine. Natural carbon has the ability to absorb between 5,000 and 10,000 parts per million gold in a cyanide solution, which goes straight out to tailings. So you can be very clever with how you process this material, but if you haven't taken this into account, then you can have trouble. On top of that, the sulfides actually do float very well, but when you make a float con, the carbon goes with it, which makes it quite problematic. We've done test work at Alfred H. Knight to generate a concentrate. We get about 95+% into about 10% of the concentrate mass, of the bulk mass, at quite a high grade. When it's at a high grade like that, you can afford to do some fairly creative things. We're looking at a number of different types of oxygenation and oxidation processes, and that's what we're working with at Alfred H. Knight at the moment. I mentioned tellurides. If you can oxidise it and then you cyanide it, you still have generally the issues with tellurides. Tellurides take between 10% and 500% longer to leach, even in a concentrated cyanide solution. So the the presence of tellurides is extremely important, especially the high silver ones. Silver is a bugger for slow leaching on its own. When you mix it with tellurides, it makes it 10 times worse. You can see here, this is a section from a piece of core. We recently did ore sorting test work with Tomra in Germany, and it was very obvious that there was carbon in the ore just from the samples. So how you ore sort is actually quite critical when it comes to a lot of the fine material that is generated during crushing and sorting and screening. You can see that some of the graphitic and organic carbon in a black shell, the grade's really good, but it's got this residual carbon, which is you really need to pay attention to it if it's in the ore, and it needs to be identified early days. Also, the locked surface of the gold particles and telluride particles is extremely important. If you look at over here, free surface, it's less than 10%. And you've got middlings and high middlings and then liberated. This is an extremely important test. So if you're looking at this line here and this line here, it tells you some fairly interesting stories very, very early on. So this can be done from first pass drilling. This can be determined. Whether you're going to spend another $40 or $50 million drilling, you really should know this information before you start writing the checks. The technology solutions we're going through at the moment, we use extensive use of handheld XRF in field exploration, and that will also be carried over into grade control. There's a number of elements, as I explained earlier, that also fingerprint, especially arsenic. This thing pops up with arsenic. We're looking at ore sorting because of the grade of the deposit. So fairly early on, Tomra will do a free test, like a 20-litre bucket of your selected samples, to see whether you can upgrade the grade from, say, 0.5 to generally as a doubling of grade if you get the parameters right and the sizing right for ore sorting test work. Fine crushing. There's a lot of interesting work that can be done if you fine crush the ore before it goes into a ball mill. Standard practice, especially people that use SAG mills, they're using rather large lumps of rock, and it takes a long time and a lot of energy to grind this material down. So we're looking at using 5 millimetres into a ball mill rather than 25, which is standard practice. That allows the ball mill to grind it much finer, which allows you to get to some of these particles, which are generally very fine, inside the rock matrix to allow access to cyanidation. And that's very important if you know how much of the gold is exposed to leaching early on in the testing. Gravity circuit is very important to take out the coarse gold and the tellurides. Tellurides, as I mentioned earlier, very slow leaching. So if you can get them out early days, you can put them into intensive cyanidation, which will actually recover the gold from the tellurides. If you leave it in circuit, you'll be lucky to get 50% before it goes through the tailings. And that, again, this Gecko inline leach reactor is one of probably the best on the market. Flotation of sulfides. If you've got a low-grade sulfide deposit, if you try to cyanide it, generally, especially this one, in some samples, we've got 5% recovery by direct cyanidation. So immediately you stop spending money on that and you start to target another type of extraction process. That's very important to feed that into your exploration models. Oxidation of sulfide concentrates. We're going through this at the moment with Alfred H. Knight in Cornwall. And this is still in the development, which way we would go here. Longer leach times. If you're doing a plant design, people will try and save capex on tankage. It's probably the most ridiculous saving of capex you could possibly imagine. The more tanks you have, the longer that dirt's in there exposed to cyanide. And the longer it's exposed to carbon to absorb the gold in solution. Carbon passivation treatment. We are looking at, there's a couple of tricks. I worked in Nevada for 5 years and I had an ore body of a similar nature. We developed a few processes to negate some of the carbon robbing characteristics of the ore. That's being reactivated in here. The filtration of tailings, you can increase the recovery by 2 or 3% by filtering tailings. And it also eliminates a lot of the environmental problems. Water consumption, especially these projects in Saudi Arabia, water is an issue, full stop. The key technical inputs are we use Olympus Vanta. We've just purchased 3 of these systems because it can allow you to screen samples before you spend the money sending blank samples off for analysis. So if you don't have a kick using the Vanta and the Rockbot, then really they shouldn't be going off unless you want to do check assays on them at a later date. Saves you a lot of money, it saves you a lot of time. And we use the Olympus Vanta on screening core samples as well, so you don't send the whole core off for analysis, which is ridiculous. Why would you have a geologist looking at core and then assaying everything? We've got these guys we used, as mentioned earlier, we've got Tomra. We've set up an early days deal with Petrolabs, where if any of the guys in the field want to find out what the mineralogy is, they can send it directly to Petrolab. We have an open account, so we understand mineralogy very early days. And then Rick Minko Consultants, he's grumpy, but he's actually very good. He's probably got as much grey hair that I used to have. This guy is very creative, working with the Alfred H. Knight. We use him extensively. The next one is a rather large VMS occurrence. It's our second main project. At the moment, it sits around 36 million tonnes in this thing of VMS. The VMS, I don't know if you've had anyone here who had much experience with VMS. If you haven't had any experience with VMS, I would suggest you keep it that way. The strike length here is that's about 4 kilometres, and there's repetitious Gossan structures down here and over here. Saudi has got a lot of VMS structures. The problem with this, and I'll go through that in a moment, is that mineralogy is particularly important. In fact, it's critical to the economics of these projects. The ore body is open at depth, this main one, the main Hawiyah deposit. There's an oxide cap on the top, which is here. You've got a transition zone, which is supergene enrichment, and then you get down to the sparklyite at the bottom, which is 85% pyrite. This is really important to understand what's going on here. This is actually very straightforward. One of the things they found with mineralogy here when it was originally studied is that the gold is less than probably 1 micron. So even in the oxide horizon, you have to grind to 30 microns to be able to have a chance to expose the gold for leaching. So it's actually a problematic ore even in the oxides. Supergene it's pretty tricky as well. Probably you get reasonable flotation response. It's much higher grade than the fresh sulfides below it, but again quite tricky and not very thick. So each of these tonnages, that's 20 metres, that's probably 10 to 15 metres, and then this thing goes down and it's relatively open at depth. If you look at this, it's a gold grain size. You're looking at less than 5 microns. So as soon as you see that, you know you've got problems on extraction. Most gold deposits that leach well, they're down around in here. So as soon as you see that, there should be at least a red flag, if not a bell, that goes off. That doesn't help. There's quite a bit of petsite in there. It doesn't have these tellurides. They don't have antimony in them, which is even worse. I worked on a project in Nevada. It actually had a name of its own deposit, goldfieldite, which is a horrific telluride. That number says it all. When it says locked, it is highly problematic. So these tests, even in early exploration, are absolutely essential. And if you're investing in a project, then you need to get this sussed out at very, very early This number in here, you're looking at microns, 6 to 9 microns. Standard grinding procedure for a flotation plant is 75 microns. Metallurgists, they get the ump if you have to go below 100 microns normally, but 75 microns is generally sort of the number. So even if you ground to 30 microns, and below 30 microns, it's considered a slime. Slimes don't float. So when you're looking at that, you know you're in for a hiding. So again, this should be part of your exploration procedures. And it's not expensive. It can be done very, very quickly. If you look in here, you've got pyrite and tellurides going hand in hand. So even if it floats, you've still got carryover. Because of the grain size, you've got carryover. So if you, in a standard flotation operation, you have to depress one sulfide to concentrate another sulfide. At 6 microns, all these things are joined together. Even if you grind to 20 microns, you've still got joined grains. So you've got sphalerite and chalcopyrite attached to each other. So you depress one, it depresses the other. So it's, you can make a float con. You can make a good copper float con, but it's 50% zinc, which you can't sell. So again, very simple test that we carried out very early on. And to be honest, we got to a point with this test work where we said, right, this isn't going anywhere. There was a lot of money spent on flotation test work, still didn't get anywhere. We looked at the Albion process. They wanted $600 million for an Albion process. And by the way, no one's ever done this before, so you've got to be first. You look at an overrun, you're probably looking at $700 to $800 million in a plant that no one else has ever done. So never be first is a very good mentality. We ended up going for roasting. So we've been pursuing the roasting test work at Alfred H. Knight. At Alfred H. Knight we get probably 90% of everything that's in there. So it's copper, zinc, silver, gold. And if we precipitate the iron from iron sulfate, because you can't put iron sulfate into a tailings dam because you have to neutralise it first. So if you selectively precipitate it, you can generate both iron oxide and sodium sulfate, both of which are saleable, which means 0 tailings dams. If you just water rinse it after roasting, you can get over 90% of the base metals, leaving the gold in the gold and silver in the calcine. So we're continuing this process. It's not completed yet, but if we'd have known this early on, there was probably $5 to $6 million worth of test work that would not have been necessary if they'd have understood the ramifications for mineralogy. So do things in pecking order. Do your mineralogy first, get a grip on the mineralogy. Once you understand the mineralogy, then that really does lead you to how your strategy for developing the rest of the projects. We are looking at other options, chemical oxidation. We're using ozone for oxidizing the Jibal-Qutman sulfides. Could be an easy way, but you need a lot of ozone for oxidizing sulfides. So I think that's pretty much it. Thank you.
Any questions?
Thanks. Adam Johnson from Transmin. Just wanted to offer a ray of sunshine maybe, that when you classify with a cyclone in a grinding plant industrially, it's not like a fixed batch time in the laboratory, and you will get overgrinding of those gold particles. So achieving that 5 to 15 micron might not be that difficult with the gold.
It's not so much the gold that's the problem. If you've got a cyanide plant and you need to expose the gold, you've got to get it down to a pretty low sizing, and it's tellurides. So we actually prefer to go on the Jibal-Qutman process. We would probably go for 75 microns. So if you've got encapsulation at 75 microns, you've got problems because it's not going to get that much smaller. 75 would be the cut. Anything above 75 would then go back to the secondary grinding circuit.
Okay, still worthwhile doing a cyclone test because you might be pleasantly surprised for sure.
Well, we're looking at different grind sizes, but
Yeah, but there's a difference between like screen or fixed grinding time in the lab versus the industrial cyclone. Like the cyclone
no,
classifies
sure.
on gravity, not just
yeah.
not just on size. So it's an opportunity.
Well, the first pass on the mill design, we would only put in -5. Anything that's -2 would go directly to the cyclones and then to the gravity plant. So the idea is not to put coarse-free gold or coarse tellurides through the grinding circuit. You want to get it out first. Thank you.
Thank you very much. The first project you were talking about, you were mentioning about the presence of arsenic.
Mm-hmm.
And in ancient days, well, sort of 50 years ago, there was a simple solution for that, and that was that you simply roasted your ore and the arsenic went off in the air. Now, in terms of environmental controls these days, that's a no-go from what I understand. So how do you see the issue of the elimination of arsenic in 2026?
Well, the process for the first project would be a wet oxidation process using ozone or peroxides to oxidize it. We're still working on that. During that process, the breakdown of arsenopyrite would generally go to some sort of arsenogerasite, which is an iron arsenic compound. We haven't done that work yet, so we're still working on what the mineralogy of the tailings would be, but the idea would to make an inert arsenic jarosite compound.
And that could safely be placed in tailings?
Correct, yeah.
Okay, thank you very much.
Yeah.
Thanks. Anthony Bennett from MSA Group. You made an interesting comment about VMS deposits, saying if you haven't worked on one, then you consider yourself lucky, kind of thing. Is that your feelings for saying that? Is that because of your experience of the challenges of the ore body itself, or is it more to do with identifying the different zones that you've got on the ground? I mean, how easy is it on the ground to differentiate these the different zones that you've got of the VMS deposit itself?
Well, if you understand how they're deposited in the first place, the proximal VMS deposits are basically a plume that come from these smokers. By the very nature of hot solutions coming into very cold ocean, you've got almost instant crystallization temperatures. So that plume would then, depending how fine it is, would gradually drift off and then settle on the ocean floor. So the very formation of that deposit is, by default, is going to be ultra fine. So the point I was making is, if you think you've got a great ore body just by using chemical analysis, and you generate these lovely models, then you find out you end up with something you really didn't want, because you're dealing with 5 to 10 micron sulfides.
Okay, understood. Thank you.
Just to continue Anthony's point, I'm sure there are some very successful VMS mines around the world. They've all been mined now, of course, and they were properly VMS. I think it's probably right to say that a little bit of a bit of folding, a bit of metamorphism, kind of moves those sulfides around and they recrystallize, and then it's a much different story.
Well, we're looking for that, funnily enough, that where you get VMS projects that have been recooked. Then that's a different animal. Unfortunately, it's not what we have. We have the original script.
Quick.
Hey, John. I see you say there you've abandoned the flotation flow sheet. Are you looking at doing ore sorting so that you roast less material, just roast the sulfide, or could you do a bulk sulfide float and then roast that so you're not roasting gang?
Well, the reason why we introduced ore sorting in the first place is at that point gold was at 2,300. things have changed since then. Our cut-off grades are much lower, and really, you're getting down towards, when I first started in the gold industry, 0.1 of a gram was in fact detection level. It's now economic cut-off grade. It's a very different story. So bulk flotation is actually quite cheap, so we probably wouldn't look at ore sorting at this price of gold. We'll continue with the test work because the euphoria we have at the moment with gold prices, it can be very short-lived. It just takes a geopolitical movement, development to actually drop the price of gold precipitously. So we would use, and I'd strongly recommend that it's done as a primary test in any deposit you develop, because the less you have to process, you have 50% capital, 50% water, 50% chemicals, 50% tailings dam. It dramatically lowers the capex and also time for development, because time is actually very important in developing projects.
Thank you very much, John.
Thanks, guys.